As you may have noticed, there are lots of different variables that we have to consider when talking about gases. So in order to make comparing them a little bit easier, we can set something called standard conditions, which allows us to report in a very specific way using specific conditions to make the gases a little easier to compare to one another. So because the volume of the gas varies with pressure and temperature, we've agreed on a set pressure and a set temperature in order to report our measurements. And these conditions are what we call standard conditions, or abbreviated STP, for standard temperature and pressure. So what pressure would you pick for a standard? Well, the pressure we set as a standard is 1 atmosphere. The temperatures may be a little bit harder to guess, but the temperature is 273 Kelvin, or 0 degrees Celsius. These are our standard pressure and temperature for reporting gases. So let's look at an example. So we've got a gas that occupies a certain volume, a certain pressure, and a certain temperature. And we want to figure out what that volume will be if that same gas is under standard conditions. Pause the video and try to solve this problem. If we look, because we have a volume, a pressure, and a temperature, we can solve for the number of moles. Now we have to do a couple conversions. Liters are all right, but we need to convert from 44.1 psi into atmospheres. And we find that this is 3 atmospheres. We also have to convert the temperature. So we have to take our 27 degrees Celsius, we add 273.15, and we have a temperature of 300.15 Kelvin. We can plug this in and find into our ideal gas equation to find the number of moles. So we'll add our pressure, 3 atmospheres times the volume of 10 liters, divided by our ideal gas constant, 0.08206, atmosphere liters over moles Kelvin, times our temperature. And we find that we have 1.219 moles of gas. Now, if that exact same gas is at STP, standard temperature and pressure, we now can use our ideal gas equation to solve under these new conditions what the volume will be. So we just calculated the number of moles of our gas. R is our ideal gas constant. Times our temperature. So remember, we're at standard temperature, which is 273 Kelvin. We divide by our pressure, and under standard conditions, that's 1 atmosphere. And we find that we have 27.3 liters of gas at standard temperature and pressure. If we have our standard temperature and pressure, and we solve for 1 mole of gas, we get something called the molar volume. And that molar volume is 22.4 liters. It doesn't matter what gas that we're talking about, but 1 mole of gas at standard temperature and pressure gives us 22.4 liters. We call this the molar volume. Do note, though, that the masses are different. So even though they occupy the same volume for 1 mole of gas, the masses will depend on our molar mass of that gas. So no matter which gas we have, whether it's helium, xenon, or methane, we're going to have the same exact volume, although the masses will depend on the molar mass off of the periodic table. Here's a problem for you to try. See if you can calculate the number of liters of oxygen from the decomposition of 100 grams of lead 4 oxide. Pause the video to find the volume. We'll start with 100 grams of lead 4 oxide. Please note that this is a solid, and so we need to convert to moles in order to use our balanced chemical reaction. We are given the molar mass of the lead oxide. Now that we are in moles, we can use the coefficients in front of our balanced chemical reaction to convert from moles of the lead oxide to moles to 1 mole of oxygen, which is now a gas. Because this reaction is at STP, we know that 1 mole of gas, and it doesn't matter which gas, but in this case oxygen, is 22.4 liters. And so now, using our molar volume, we can calculate that we would have 4.682 liters of oxygen produced from this reaction. Can you think of any reasons why we would want to produce oxygen? Well, it might be helpful in an emergency situation if there is no oxygen around as a life-saving method.